Hi, this slideshow is on circuits that have multiple resistors in them and how do you mathematically and conceptually solve these circuits. So before we get into it, I want to go through just two common sense circuit rules. The first is that electrons are only going to move in complete circuits. That means they only go through wires that provide a route back to the battery. And that we're not actually gaining or losing any electrons in the circuit because of conservation of mass and charge, which means that the same current is always going to go out of the battery as comes back in the other end of the battery. The second is that the total energy used up in the resistors every second must be equal to the energy provided by the battery every second. So this is conservation of energy. That means that as they pass through the circuit, all electrons are going to use up all their energy and return to the battery without any energy left. Before we get into more complicated circuits, let's talk about just creating a tool that helps us track information for all of our circuits. And that tool is going to be called a VIRP table. VIRP, of course, stands for voltage, current, resistance, and power. That's kind of a cursive P. I know it looks weird, but anyway. And then when we make our VIRP table, we want to make one column for each resistor in our circuit. And when we get to multiple resistor circuits, we're going to add one additional column which represents the entire circuit. Since the entire circuit in this case is just one resistor, we can skip that extra step for now. But anyway, we make this VIRP table, and we're going to go ahead and just fill it out. So when I look at my circuit diagram, I know right away that the voltage provided by that battery is 9 volts, so I'm going to put that in there. And I know that the resistance is 100 ohms. This is the goal in a VIRP table, is to get two known values in any column of that table, because once you know two known values, then we can use Ohm's law and the power equation to solve for the other two, regardless of which two we know. So now that we know voltage and resistance, we can go ahead and use Ohm's law, I equals V over R, to solve for the current, which is going to be 9/100ths of an amp. And we can use the power equation to solve for power, which is I times V, or 81/100ths of a watt. So there we go. We've got our entire VIRP table going down there. Remember our common sense rules. So current is going to be the same everywhere in the circuit. So if we have 9/100ths of an amp leaving the battery, that's the same amount is going to go through the resistor, and the same amount is going to return to the battery. And the power that's used up at that resistor, 81/100ths watts, that must be exactly the same amount of power that the battery is putting out every second by conservation of energy. So when we move to more complicated circuits, we're going to have more than one resistor in those circuits. There are fundamentally two different ways you can hook up multiple resistors. One of them is known as a series connection, and that works just the way a series of books or a series of movies would work, where the resistors come one after another. So in other words, the electrons leaving the battery have to go through those resistors in order before they can get back to the battery. So if you think about deeply what the variables mean and how those electrons and energy is interacting at the level of the circuit, you'll realize that electrons in a series circuit have to go through all of the resistors before they return to the battery. They don't have a choice. There's a single path to get back to the battery. And since we're not allowed to create or destroy electrons, that means we have the same current through each resistor that is in series. The voltage, on the other hand, which is the energy we got at the battery, that is going to be used up along that path, right? We've got to use all our energy before we come back to the battery, but there are two places we have to put that energy in that first circuit. The second one shows 4 resistors. But in any case, so the electrons are going to use up part of their voltage in one bulb and part in the other, so that you've used up the total voltage by the time you get back to the battery. And note that if the resistors are not equal resistances, we are going to be using more voltage at the larger resistance values according to the relationships we've seen in Ohm's law. So the voltage is split between the resistors, but is going to add up to the same total. The other way you could hook up multiple resistors is known as a parallel connection. And in parallel, the electrons actually have a choice about which resistor they want to go through. They don't have to go through them both. If you think about this as a school day, you're taking one test or the other test, but not both. Or in that schematic shown on the right, there are 3 resistors in parallel, so you can choose between the 3 of them. If you have a portion of a circuit that's set up this way, the current is going to divide. The number of electrons are going to divide on those three paths because the electrons are choosing different paths. More electrons are going to choose easier paths, but some electrons, or smaller resistors, some electrons are going to go to all of those resistors, unless one of the resistors is value 0, like a plain wire, in which case all of the electrons will take that path. So as far as current goes, the total current in this circuit is not going to be the same in every pathway, although it will add up to the same total that is coming out of the battery if we want to conserve mass. And the current is inversely related for the resistance. So if one of the pathways has twice as much resistance as the other, it's going to get half as much current, according to that inverse relationship. Since each electron in the parallel circuits I drew above only has to go through one resistor before it gets to the battery, those electrons are going to be using all of their energy in that single resistor. So the voltage is going to be the same in this case, regardless of the resistance values, because there's only one place to use up that energy, so electrons use it all there. Okay, let's go through a sample series circuit and a VIRP table for this circuit. As I mentioned before, you want to draw one column for each of the resistors. So I have 2 resistors in the circuit, and I want to add another column for the total because this is a circuit with more than one resistor in it. That total kind of represents the overall simplified circuit, or you can think of it as what's happening at the battery. There's a few different ways to think about that column. The first thing that you're going to do is fill in all the known values. So we know R1 is 100 and R2 is 200, and I know that the voltage provided at the battery is 12 volts. So we're not at a place where we have 2 known values in any one column, so we need to figure out another thing. Now, if you think logically about this circuit, you realize that every electron going through the circuit has to go through both of those resistors. That should increase the resistance of the overall circuit. Or you can think about the resistivity of putting 2 resistors in a row, right? We have to go through a longer resistor, therefore it's going to be a harder resistance. It would make sense if we just added together the resistance value of those 2 resistors, and it turns out that is actually what happens. That means that the total resistance in this circuit is going to be equivalent to 300 ohms because we went through a 100 ohm and a 200 ohm resistor in series. There actually is an equation on the equation sheet that shows how to do this. RS, which stands for the resistance of a series of resistors, is equal to sigma, means the sum of all of the individual resistors. So in other words, add up R1 and R2 and any other resistors you might have in series, and that will tell you your total resistance in series. So the good news is we now have 2 variables in our total column. We have voltage and resistance, so we can calculate the current coming out of the battery is 0.04 amps, and the power at the battery is 0.48 watts. Here's where the physics come in. So I want to think about how do I get a second variable in those other 2 columns, in R1 or R2. And I realized that in every series circuit, because there's only one path for the electrons to go through, every electron has to go through each resistor. That means if 0.04 amps of current leave the battery, I know that 0.04 amps of current have to go through R1, and the same current has to go through R2, because otherwise we would be losing electrons. So I can fill out those 2 current values as well. And now I have 2 values in those 2 columns, and so I can use my 2 equations, Ohm's law and the power equation, to calculate out the voltage values and the power values. Once you've got your whole table completed, it makes sense to look at each row of values and think about whether those values make sense from a conceptual level. So when I look at these voltage values, I notice a couple things. First thing I notice is that 4 and 8 add up to 12. Does that make sense? Well, it does, because if I got 12 volts of energy at that battery, I have to use it all before I come back. So if I'm going to use 4 at one, I better use 8 at the other to use it all up. The other reason it makes sense is you notice that we're using more voltage or more energy at the larger resistor value, okay? Because there's a linear relationship between V and R if I is constant, as it has to be in the circuit because we only have one path. And the ratio is actually 2 to 1, just like the resistance ratio is 2 to 1 as well. So we calculated those values with our equations, but it turns out we probably could have figured them out logically using relationships and ratios of the resistance values as well. So there's usually multiple ways to get to your solution. The current row makes sense because, as we said before, electrons are conserved. We can't gain or lose them. There's only one path. Therefore, we have to have the same current everywhere in the circuit. The resistance values make sense because if you have to go through two resistors back to back, that's going to be a harder overall resistance. It's like adding more length to a wire. It's got a larger resistivity. And the power makes sense because power fundamentally is energy every second. And what we see is we're going to have to, the battery is spitting out 0.48 watts of power. That energy has to go somewhere, right? It has to be used up somewhere. So if I add up 0.16 and 0.32, you get 0.48, and that is a demonstration of conservation of energy. If you were asked to tell which light bulb was brighter, the answer is R2. You can see that right here. It's a 0.32 watt bulb as opposed to R1, which is a 0.16 watt bulb. And if you were asked to explain why, I would say in a series circuit, when the current is the same for both, the bulb that has a bigger voltage is going to have more power, and that happens to be the bulb with a higher resistor in this case. All right, let's talk about a parallel circuit and how we would make a VIRP table for this. I'm going to put the same two resistors in there so we can compare and contrast these circuits, but this time they're going to be in parallel instead of in series. So your VIRP table starts out pretty much the same way, a column for each resistor and one for the total. And in fact, the values you put in are going to be the same as well. I know that R1 is 200 and R2 is 100, and my total voltage is 12 volts. But there's where the similarities end. Okay, everything else depends on the way the variables are hooked up. So for example, it wouldn't make sense to say that my total resistance is 300 in this case because the electrons don't have to go through both of those resistors. This is not a difficult school day, or this is not a difficult circuit for these resistors to get through because they have a choice of paths. Actually makes it a pretty easy one. So I can't just put in a 300. You gotta not get in the habit of doing that. You gotta think about whether it makes sense to put it in. So if I can't put that in, where am I gonna go? Well, if you think about what's happening at the level of the circuit, you'll realize that each electron gets 12 volts of energy from the battery. And each electron only has to go through one of those resistors before it returns to the battery. That means there's only one place for those electrons to use their energy, and they have to use it all. So the electrons that choose to go through R1 have to use 12 volts of energy. And the electrons, which are different ones, that choose to go through R2 also have to use 12 volts of energy based on that path that they've chosen. So now I have two values in my first two columns, and I'm going to go ahead and use Ohm's law and the power equation to solve for I and P. So I is going to be 0.06 amps there, 0.12 amps there, and my power is 0.72 watts and 1.44 watts. All right, so my table, I'm making progress on it. I just need to get one more value in my total column before I can calculate the rest. So for me, there's a couple different places you can go with this. One option is say, well, I know that energy has to be conserved, so I actually could just add together my power values and put that as my total power, and that better always work or we've got a problem. But I tend to not do that first because I like to use that as my check at the end to make sure everything worked out. So I tend to think about current next. And what I think about is if 0.06 amps of current are going through R1 and 0.12 amps of current are going through R2, how much current had to kind of come into that junction to make that happen? Like, how do I get that many electrons through those guys? What had to come in so that I could break it into those two parts? So if you think about it, you'll realize that the battery has to be spitting out 0.18 amps of current in order to allow that current to divide where it divides and goes through R1 and R2. So I put in 0.18 amps for the total current. And now I've got my two values, and I can go ahead and calculate the other ones using my equations. I get an R value of 67 ohms, and I'm going to get a power value of 2.16 watts. Now that I've got my whole table filled out, I want to go and see if each one of those rows makes sense, just like I did with my last circuit. The voltage values here are a little different, but they still make sense because each electron is only going through one of the two resistors. Therefore, they have to use all of their energy in that resistor, which is why all of those energy values are the same. The current makes sense because different electrons are choosing each path, but the total current is going to add together to be the total amount that came out of the battery. You'll also notice that the higher resistor, R1, got less current than R2 by a ratio of 1 to 2, because electrons will generally choose to go through the path of less resistance. There is an inverse relationship between the amount of resistance and the amount of current through that path. The resistance value makes sense because adding two resistors in parallel makes an overall smaller resistance in the circuit. So 67 ohms is less than either of my individual resistors. If you think about the resistivity equation, it's like taking two wires with different diameters and putting them together into a single slightly bigger wire. That wire is going to have less resistance than either of the original wires because there's more area for those electrons to flow through. And the last one is power, and I always do this last because I know I've done my circuit right if I see that energy is conserved. 0.72 plus 1.44 does indeed give you 2.16 watts. You should also notice that if you're asked which light bulb is brighter, in this case it's R2 because it has a higher power rating. But the reasoning is totally different because in this case it's the voltage that's the same, and therefore the bulb or the resistor that has more current is going to be the one that is going to have more power. And it's actually the opposite bulb than was powerful in our series circuits. So that's pretty important. One last thing I want to mention about parallel circuits is we calculated that resistance value, that 67 ohms, indirectly by working our way through a VIRP table, but there is a direct way of calculating that from the beginning if you want to save yourself some time. The equation to use I just put up on the slide, and it's on the AP equation sheet. 1 over RP equals sigma of the individual values from R1 to R2, or however many resistors you have in parallel. So in other words, the reciprocal of the parallel chunk is equal to the sum of the reciprocals of the individual values. So the way this would work if I wanted to solve it directly is I would say 1 over R, which is my total R for my circuit, equals 1 over 100, so my first resistor, plus 1 over 200, which is my second resistor. So if you add 1/100th and 1/200th, you get 3 200ths, okay? And from there, you have to take the reciprocal of both sides. So 1 over R is 3 over 200. That means R is going to be 200 over 3, which is the same as 67 ohms. So this is another shortcut, a way to get to that 67 without doing the entire VIRP table first. I want to pause and do a little bit of a compare and contrast on series versus parallel circuits, which comes up a lot on these tests. In series circuits, you found that the higher resistor bulb was brighter because when current was constant, more voltage made more power. You also found that there is more overall resistance in the circuit, which actually means less overall current in the circuit and less overall power. We didn't really talk about the overall power value, but if you look back at your notes, you'll see that there's a lot less overall power in my series circuit, even with the same bulbs and the same battery, than we see in the parallel circuit. The other thing about series circuits is that if you put a switch anywhere in those circuits, it controls all the bulbs in the circuit, which could be a good thing if you want to turn them all off, but more likely it's a bad thing because if one of the bulbs burns out, everything in the whole circuit goes out. Parallel circuits, on the other hand, have the flip relationship. The lower resistor bulb actually ends up brighter when you hook things up in parallel because when the voltage is the same for both bulbs, more current means that bulb is going to get more power. There is also, if you think about the circuit level, there's less overall resistance in the circuit, and that means overall the circuit gets more current, and that's going to contribute to that circuit overall distributing more power as well. You also can set your switches up so you can have individual switches on individual resistors. This ends up being really handy, like for example in a house, because you don't want one switch to turn off your toaster and your coffee maker and the lights. You want to have individual switches or individual plugs for those devices. So long and short of it is, houses use almost exclusively parallel wiring because of all of these benefits. You might think that less power is good, but that actually means our devices don't work as well. So we want to be able to draw as much power as we can quickly. The other thing about a parallel circuit is that the individual devices actually don't impact each other. If you do a VIRP table adding resistors in parallel, you'll find that the original resistors actually are not affected by adding additional resistors. That affects the total current in the whole circuit, but putting another light bulb in doesn't make everybody else dimmer, which is a good thing. So parallel is by and large the way to go for wiring. The one catch is that parallel requires a lot more wire, which is kind of more expensive. So there are a few times we use series only when we don't really care too much about the devices, like holiday lights. So it's also possible to have a complex circuit. And a complex circuit contains both series and parallel portions nested inside of each other, okay? The good news is this is not a whole new kind of circuit. I don't need a whole new set of rules. I just need to follow the set of rules that I've already created for how to deal with series and parallel components. For example, I'm going to recall that the current has to be the same through any series portions of the circuit, right? So the 3 ohm resistor is in series with the 6 ohm resistor, and actually that 5 ohm resistor on the bottom is in series as well. They're all part of the same path. And electrons must go through all 3 of those, therefore we consider them in series. So we know that the current through those 3 resistors is going to end up being the same, and also the same as the battery current, because all of the electrons that leave the battery are forced to go through all 3 of those resistors. So when I make my VIRP table, eventually that is one rule I can follow for those 3 resistors. And I know that the voltage is going to be the same across any parallel portions. So for example, that 12 ohm bulb and the other 6 ohm bulb are parallel with each other, which means the voltage drop has to be the same for those 2 resistors. The amount of energy the electrons use in the 12 ohm path is the same as the amount of energy they use in that little 6 ohm path, because we have to use the same amount of energy going through the entire circuit, regardless of which path we choose. A couple last tips I want to leave you with if you're faced with a complex circuit, which comes up pretty regularly on these tests. One is that it often helps to redraw and simplify your circuit by replacing 2 or more resistors with a single equivalent resistor by using our resistance equations to calculate how big would a single resistor be that does the same job as the multiple resistors in the circuit. So for example, that first circuit on the left, which we saw on the last slide, what you can do is you can imagine pulling out that little parallel portion, because we have a chunk that's purely parallel, right? The series portions are a little bit complicated because they're in series with this weird parallel piece. But the parallel piece is purely parallel. So I can imagine pulling out those 2 resistors and replacing them with a single resistor. And I would use my parallel resistance equation to figure out what the value of that single resistor should be. So 1 over 12 plus 1 over 6 gives you 0.25. 1 over 0.25 gives you 4 ohms. So this second diagram is an equivalent diagram where I've removed a parallel portion and replaced it with a single 4 ohm bulb with an equivalent resistance. I can do this one more level, right? I can actually simplify the circuit down to a single resistor because now I have everything in series with each other. So I can use my series equation to just add up the value of those 4 resistors in series and come up with an equivalent resistance for the whole circuit of 19 ohms. This is really useful because if you're making a VIRP table, often you want to put in that total resistance in my total column. That gets me 2 variables over there. Usually you know your battery value and then you got your total resistance. And so now we can start getting current and voltage and we can start working our way back into the more complicated circuit. So you just want to use relationships, equations, logic, all of the tools that you have to try to fill out the rest of the VIRP table. At the very end, though, you do want to double check to make sure the individual resistance power values add to the power dissipated at the battery. That is going to be true no matter how complicated your circuit is, because that battery spits out a certain amount of energy and it all has to be used every second by conservation of energy. Okay, thanks for watching. Please take a minute to review the essential question, which is how can I organize my data and use equations to predict the behavior of complicated circuits?